Okay, well, thanks everyone for coming. My name's Austin. I work at Anagram. I was previously at Metaplex, where I led the protocol there. Today, I'm here to talk to you about verifiable compute. Title of this presentation is MIP equals NEXP, which is kind of the foundational discovery that sort of led the human race into thinking verifiable compute was possible. Basically, this says that the types of things that we can do with mathematical interactive proofs are in the domain of problems that are very, very, very complicated. So we can do very complicated computations, and we can prove them with mathematical interactive proofs. So the fundamentals of why people are doing verifiable compute is pre-internet math nerds are looking for ways to verify these big fridge computers that they are working on are doing the right thing. Post-internet ideas are essentially like, okay, now we have this explosion of machines doing compute. We really need to make these verifiable compute schemes more efficient so that we can move trust into different areas. Today, we have so much of our data, so much of our computation being outsourced to parties that we don't have any control over or understand or have any way of verifying they're doing the right thing. And now we have systems that not only use our data, but we have banking systems and we have blockchains where our money is basically data moving around. And so the reward for all of our hard work and some of the source and enjoyment of our life is like bound up into these systems that we can't control and we have no way of verifying. So the fundamentals of why is, it's a pressure from the world and users and academics to figure out how we can prove computers are doing the right thing. Verifiable compute is like everywhere and nowhere is my sort of supposition. As I said before, we have tons of consensus mechanisms, which is a form of verifiable compute. We have tons of sort of like commitment schemes, which is a very, depending on how you squint, like a verifiable compute system with Merkle trees and different things. I maintain that verifiable compute and more succinct, which means like a easy to verify statement of a complicated computation is needed for efficient consensus algorithms, and it's needed for efficient blockchains. Modern blockchains, a lot of them rerun the smart contract runtime many, many times before they even hack the block, right? Ethereum does this. I mean, Flashbots. I mean, I don't, I think Cheeto to some extent is doing this as well. Like, and on Solana, like, the leader is probably the only one executing things, but if you want to rerun and you want to like check everything, you need to rerun all of the state transitions yourself. They also require storage for the verification, right? So consider like Bitcoin versus Mina, right? So if you want to like verify the entire history of Bitcoin up to the current state, you actually need to go grab, however many gigabytes of data. And you need to do the Bitcoin hashing all the way up and check and see if it's right. But Mina, for example, you don't actually need to have that. Mina is another blockchain. You should go check it out. 3-minute block times is sort of a huge letdown, though. So you're going to go get super excited about it. Then you're going to build a ZK app and you're going to like submit it. And you're like, wait, 3-minute block times? If you're coming from Solana, that's just dead on arrival. If you're coming from Ethereum, hey, maybe you're good. Maybe you're not good. Who knows? Mina, you don't need any data. You just need the Genesis block, which you have to find that from a trusted source, of course, a source that you can find, but you can get that from multiple sources and double check to see if it's correct. And you need the most recent proof. And then you're not necessarily trusting that you got the right 500 gigabytes of data. You don't need to keep 500 gigabytes of data around. You basically just need the verification key, Genesis block, and the most recent proof. The only reason you would need the verification key is because you can actually derive the Genesis block from the verification key on Mina, which is kind of cool. So there's only like one artifact there, trusting that's the right verification key that matches up with the circuit. Ethereum today, they select validators from this sort of like thing called RANDAO. You probably know about it. I love that Ethereum Foundation is doesn't even accept a 1-bit bias, because there is a scenario where you can get a 1-bit bias in the random selection of the committee, and that's not good enough for them. I think that is, as much as we all have feelings toward Ethereum, like I think that is incredible that they don't accept that, because they want completely decentralized. I was about to say trustless and break my own rule. But soon they are working on using a verifiable delay function instead of RANDAO, which is kind of like everyone coming together to provide randomness. A verifiable delay function would be something where the locus of trust is just moving to, okay, do we all agree and accept that this verifiable delay function is the one that we're using? And if enough of us agree, then that's the one. If a few of us disagree, then we can kick them out, kind of thing. A VDF is kind of like a tiny localized proof of work algorithm, but it's a form of verifiable compute, because you're verifying that some computation was run over and over and over again, and that takes a requisite amount of time generally, and time being like computer time, not necessarily wall clock time. Consider Solana. I mean, the announcement went out the other day. Light Protocol are using zero knowledge proof systems to allow state transitions to remain compressed, but still represented on Solana. And they have some cool functions to compose things together. And I'm sure, like most things on Solana, are new, and it's just a big punch straight into the face of all the RPC providers, because then it just increases what they have to do. But who cares about them, right?